Hello.
Let us react.
Yes, we're going to teach you about some reaction symbols and notations and types of chemical reactions in this lecture.
4 of them. So you will be able to classify reactions as either synthesis, decomposition, single or double replacement, and understand said chemical notation involved.
Because what a chemical equation is, and I think this is one of the first times we're really going to see them, is it's a recipe, and you have to understand all the individual parts actually mean something. If you don't understand these notations, you're going to be like, huh?
Everything we've done so far this year is built up to this point, and we will rely on all of it to get us through.
So how do we write a chemical reaction?
Well, we start with reactants on the left-hand side. Please, can we get this right?
Every time.
Please. So in this case,
we've got 2 hydrogens and 1 oxygen. 2 moles of hydrogen gas and 1 mole of oxygen gas. Those reactants would be on the left. The arrow that we show says this stuff that was reactant reacts to form, makes a chemical reaction with. And we finish
the products
on the right.
So what you're going to see is really just all this without the words.
Right.
But you need to be able to, and we did it earlier in the unit,
in vocab,
be able to, right after it, right? We were able to write these chemical reactions out with words.
Right. So 2 moles of hydrogen gas combined with 1 mole of oxygen gas and react to make 2 moles of H2O, water, dihydrogen monoxide.
Right. Now, he just said it because he knows the phases in there. Let's not stress about that.
That's true.
That's what it means.
I did say gas because I know that hydrogen and oxygen are diatomic gases.
Right. And the neat piece there too is that we know that those 7 diatomics are diatomic. So just because it says H2, you don't have to say dihydrogen.
Right.
You can just call it hydrogen because once you say that, we know it's diatomic. It has to.
Absolutely. That's what chemists do. They know things.
We know things.
Coefficients will tell us how many moles of each species. Just like I was literally narrating to you, I said 2 moles of H2 plus 1 mole of O2. That tells you how much of each little package, ingredient, reactant, and product are involved.
Very good. Then we have the amounts of reactants and products. So in this case, we can talk about the number of atoms. So the number in front of Fe2O3 is 2. That means there's 2 molecules of that stuff. So I can follow the picture along. When I distribute, it's actually 4 irons and 6 oxygens. Atoms, not molecules. Right. Atoms, right? So the coefficients tell us how many moles of each molecule follows.
Absolutely. So
the subscripts, though,
they tell us how much atoms of each type are directly in front of it. That should kind of be reviewed.
Kind of is.
Yeah. Right? So let's move on to the next little piece that we've got to do. Phases of matter.
Here we go.
These notations are usually shown in script, so like, cursive style. S means solid. So whatever that material is, like if there's an S in parentheses after it, it means that it's a solid version of it.
Yep.
L
liquid.
for liquid.
Yep. You will usually see these too.
G would tell us not solid, not liquid, but
gas.
Gas.
And not grams.
No.
Specifically gas.
No.
AQ is the one we will see the most.
Aqueous.
Specifically dissolved in water.
So what it means is that material, whatever it was and however many moles of it were there, are dissolved in water or as a solid or a liquid or a gas.
Correct.
So it's different than the parentheses for
liquid.
Polyatomic ions.
That too. But these are also subscript style. So these are done small. You'll see them, they're real little.
And always at the very, very end of the molecule.
Of each molecule. Correct. Yep. So we're good there.
Energy can show up in chemical reactions too.
As a product or a reactant, we simply just treat it that way.
Okay. So there's just a generic picture of a reaction showing the reactants, the products, and the states of material.
Yeah, with the solid, the liquid, and the gas.
Right.
There you
go. So delta H sometimes shows up.
Enthalpy.
It's the heat of the reaction. Either reactions heat up or they cool down. Sometimes they'll be written after the overall reaction.
You guys have seen these delta H's in your reference table quizzes.
Yep.
We haven't done the unit to really break down what that's going on, but know that there is heat involved in some way. And we usually measure that in kilojoules per mole.
Right.
And that's the units for said delta H. What we're going to get into eventually is negative delta H,
positive delta,
positive delta. Oh, see what
here we go. A little taste of it first. Sure.
See?
So an exothermic reaction is when heat leaves a system. So a delta H value would be negative and be written after the equation. So this plus that reacts to makes that. And then a delta H over on the other side tells you if it releases or absorbs energy.
Sure. And it could be written as just a number. as an actual product could be 65 kilojoules.
Right.
Well, that means heat, and then it's on the product side. So you need to know that when you see heat on the product side, it's exothermic. So if that isn't written down somewhere on the side of this paper,
you should.
Ooh, yeah, because that's muy importante. I mean, that is going to come up for the rest of the year.
Now, endothermic reactions are opposite. Heat enters the system and the delta H values are positive, and in a chemical equation, you would see heat on the reactant side. Like this material plus that material
Plus heat.
absorbs some heat, then reacts to make that material over there.
Right, like cookies.
Yeah.
You need to add heat.
Right. You can
So
mix
that
it all up
recipe-
all you want, but if you don't heat it, it doesn't react.
Right. And so then again, that you could see the number with kilojoules as a reactant. That's going to tell you we're adding heat into the equation. So adding heat is endothermic.
Yep.
And the way we remember this is the exit, right? Exo is closest to exit.
And that's always on the right-hand side, the product side
leaving.
of a reaction. Mm-hmm.
Right.
Catalysts can be in reactions too, and usually when a catalyst is there, it'll be written over the arrow. So this example, the sulfur dioxide and the oxygen are reacting if there's a catalyst to produce sulfur trioxide.
And the reason we write it over that is by definition, a catalyst is never consumed in the reaction. It will always be there. It's like recycled.
Mhm.
So it doesn't turn into anything else. So we write it above the actual arrow because not only do we need it to produce the reaction, it won't actually be a player. It just makes the reaction go.
Exactly. Mm-hmm. So the generic types of chemical reactions, we usually put little codes to track the movement of the elements in a reaction so that we can decide if it's a synthesis, decomposition, single replacement, or double
You want
replacement.
to code up the first one, and then
Sure.
we'll just kind of get going fast through the rest. So the generic equation here is A plus B becomes AB. And in this case, we give each species the code, right? So if we see the first species there, we call it A, we call the second species B, and then it becomes AB. And if you notice, that becomes what we showed you as the generic. By coding, it's exactly the same thing. Okay, I got two things that come together to form one. Definition, synthesis.
Yep.
Cool.
What else we got?
Decomposition's the opposite. I got one thing that reacts to form two. So in this case, I still see a P and I see an O. So I go ahead and do PA and BO, and I see that BAB, they're together. So I just write them together. Then on the other side, I have the symbol. So I do the A plus the B, and then this matches that equation. So
That's
what
we're doing when we code reactions. That's how we recognize them so quickly, is we're just doing it in our head. We're like, oh, well, there it is.
Yep.
You'll get there too eventually.
And the POGO actually is really cool about the prom. It helps us figure these things out. So single replacement, the generic code is AB plus C goes to CBA plus A. So in this case, we'll say AG.
For AG.
Yep. N is going to be B.
And
CA would be C. So C would be CA.
And B is actually NO3, Mr. Noakes.
Oh, yeah, you're right.
So I'm going to just code it up like that. So I got A, B is NO3, AB plus
C
C,
becomes
making, well, I got C,
C.
CB
B,
plus
A.
A.
And you can see that the C and the A switched. And so that is single replacement. I have you'll see an atom or an element with a compound, single replacement.
And notice I actually used one code for the entire polyatomic ion, and I'm
Yeah.
about to do the same thing.
Yeah. Yep. So Na is going to be A, and B is going to be NO3, and C is going to be Ca, and D would be SO4. And we're going to get AB plus CD goes to CB plus AD. Oh, and that is actually our code. We have AD and CB switched, but that's okay. It still matches.
Because of the commutative property of mathematics,
You
when
got
you
it.
add things, it doesn't matter what order you
Nope.
add them
3
in,
plus
they always
2
become the
and 2
same
plus
thing.
3. Yep.
So that's a little connection to your math class right there. It doesn't matter what order you have in them, CD plus AB, or becomes BC plus DA. It's the same thing. We're swapping two things around.
I think.
Just in time.
Whoa! See ya.
I click the button and I turn it on.